Welcome to lecture number 49 on electrical machines 1, and we have been discussing about parallel operation of transformer, which is an important topic. And recall that we in our last class I took an example and told that suppose you have got two transformer, one transformer is transformer A, another is transformer B. Then if you want to connect them in parallel, what does it really mean is that connect the primaries of transformer A and B parallel and energize with its rated voltage. Of course, before paralleling, we must ensure that the voltage ratings are same, primary voltage and secondary voltages are same. Then only you can parallel, otherwise not. Similarly, the secondary coil voltages of transformer A and transformer B, they are connected in parallel, and that will be used to supply the load. Now, the necessity of connecting two transformers in parallel, we also discussed that and told that in case you have a single transformer supplying a load, and if the load demand has increased, then you must purchase another transformer of higher kVA. Instead of doing that, purchase another transformer of lower kVA, but having same voltage ratings and connect them in parallel. So, that the old one you are not just moving from the circuit. So, in this way as demand increases, perhaps you can connect two or more transformers in parallel and supply the new load demand. Each one will contribute to the load. As an example, I told that suppose you have two transformers of voltage rating 400 volt and 200 volt, and one transformer rating is in the next page, perhaps I wrote. Okay, these two transformers you are connecting in parallel. Now, also voltage rating should be same, and while connecting them in parallel, we must ensure polarities. Same polarities must be connected both on the primary and secondary side. So, this was actually that polarity. This will ensure plus here. Okay. In general, EA and EB may be slightly different, because after all these two transformers are two different transformers. Exact matching of the secondary voltages when primary is energized with rated voltage which are connected in parallel is very much unlikely. But nonetheless, let us assume that the secondary voltage as a general case, suppose the induced voltages are EA and EB. And for this transformer, it will be close to 200 volt, this will be also close to 200 volt, and these two voltages will be there, and there is load connected. This is your load impedance, and all the equivalent circuit parameters are referred to the secondary side, to the load side. And so, transformer A equivalent circuit is simply EA, REA, JXCA, and so on. Here also EB, this one. Then we would like to know that this is a simple circuit otherwise, that this circuit is to be solved, but we will be interested to note for a given load current I 2, suppose this is known, then what will be I A and I B, that is how these currents will be shared. And in case of transformer, you know, current ratings are kVA ratings only, voltages are maintained same almost. Therefore, whenever I say current ratings, it means their voltage ratings. So, kVA ratings. So, then we just found out these expressions that for a given I 2, if this is known, your IA will be this much and IB will be this much. In general, if EA and EB are not equal, it will be a general expression like this, but since EA and EB will be very close. So, and if they are absolutely equal, then of course, IA will be equal to simply this and this one. That is this part, this second terms will be much higher compared to these terms. So, approximately IA will be this and IB will be this. Why approximately? If EA equal to EB, this will be the case. Even if EA is slightly different to EB, I can calculate the exact values, but also this will give you an idea how IA and IB will be. Mind you, these are all phasors here, IA, I2, IB, I2, I2 is known. Now, the ratio of IA and IB has become equal to JDB by JDA. Okay? So, up to this point we have done. Therefore, we have seen that in the transformer it has come like this, IA by IB is equal to ZEB by ZEA, is not, which also means that this is phasor relationship. This also means that magnitude of IA is to magnitude of IB will be equal to magnitude of JDB divided by magnitude of JDA. That is how it will be shared. Okay. This equation is very important. From this equation, we will also put another conditions for those two transformers A and B for better load sharing. And what is that condition? That we can get from this equation. That is why this equation is important. Now, what is that? So, suppose you have two transformers, suppose transformer A is of rating 400 volt stroke 200 volt 50 hertz, and transformer B has got a same voltage rating, it must have 200 volt 50 hertz, that is fine, and the kVA rating of transformer A is suppose 4 kVA and this transformer rating is suppose 2 kVA. Okay. Therefore, rated currents of transformer A on the low voltage side, how much it will be?
1020.
Huh?
1020.
This will be 10.
That is 20.
This is 20 ampere, this side current, and this rated current is 10 ampere. So, this information I have. Similarly, rated current of this side will be 10 ampere and this side high voltage side current will be 5 ampere, is not. But anyway, we have referred everything to the LV side. We have connected the secondary side 200 volt side in parallel. So, so this is the thing and this is the circuit, that is this is one voltage source, this is JDA, this is another voltage source on the secondary side, this is JDB and these two are in parallel, Z2. And this is what I told your I2 load, and this is IA and this is IB, and this is EA this is E B, and assume E A is equal to E B, that is both are 200 volt is equal to 200 volt. Okay. So, that is fine. Now, I have this relationship. Okay. We see that for a given current, load current, the current shared by transformer A and that of transformer B are in the inverse ratios of their respective KVAs, that is current shared by transformer is proportional inversely to its leakage impedance. I A is proportional to 1 by Z D A, is not. So, it is proportional to inversely proportional to leakage impedance. Now, what is the important thing? See, here I would like to have our intention will be, I told you in the last class as well, that when see transformers whenever it is in operation, it is always nice to operate the transformer as full load. It will, because that is why your investment will then become meaningful. Why then purchase so much kVA, so much voltage transformer. Therefore, when these two transformers are operating in parallel, I would like to have 30 ampere is supplied to the load and 20 ampere is carried out by transformer A, and at that time and 40 ampere is carried out by transformer B. That is the most I mean best thing one can think of, is not. So, if I 2 is equal to 30 ampere and I A is equal to 20 ampere and I B is equal to 10 ampere. If this happens, that is the best thing. All transformers will be under full load condition, KVA handled by transformer A will be then whatever its KVA, 4 KVA, transformer B 2 KVA, and KVA supplied to the load will be approximately 6 KVA. Nothing is better than that. Okay. Therefore, but we then find that I A by I B is Z D E by Z D A. Therefore, you see the ratio of I A by I B here, I A by I B, this demands that I A by I B ratio should be 2:1, is not? If this best thing to happen, then I A by I B must be 2:1, which means that 2:1, which implies that the impedance of transformer B should be twice the impedance of transformer A. From this now, therefore, if therefore, Z E B must be equal to twice Z D A, then only such a thing is possible. If, for example, it is the other way around, that is, suppose you find you have purchased 2 transformers and you find that Z D B by Z E A is equal to suppose half, just opposite. Leakage impedances are like this. Then what is the implication? Implication is, see the ratio of the currents I A is to I B is to the total current I 2, this ratio. My desirable thing is it should be 3:2:1, that is what I want. But if it is other way around, then the ratio of currents will be just opposite. The transformer having higher kVA is having higher impedance, is not? The kVA of this transformer is 4 kVA. Higher kVA transformer must have lower impedance. Otherwise, what will happen? The moment you start loading, the transformer which is capable of supplying more current, for a given load current, it will always take less current, and the other transformer which is lower kVA will share more currents. So, a situation will soon occur, the transformer B having lower kVA will carry rated current, and transformer A has not yet reached rated current. I think you have got the idea. This is very important. Therefore, I should then now add another important point, that is, if you want to have meaningful parallel operations of transformers, then I will say voltage ratings must be same. kVA ratings may be different. Obviously, why kVA ratings should be same? kVA ratings is different, but I will demand the transformer leakage impedance should be inversely proportional to their kVAs. So, I must have transformer leakage impedance should be inversely proportional to their kVAs. Then only you get this nice division of load currents. Now, mind you, the ratio of the currents, magnitudes of the currents is JdV by JdA. Now, I say that okay, magnitude of the impedances, leakage impedance should be inversely proportional to their kVA ratings, fine, but JdA itself, you know, ZEA is what is inside? It is REA plus JXEA, all with respect to secondary side. Similarly, JdB is equal to REB plus JXEB, and I saw that the magnitude of JdA, which is equal to root over of REA square plus XEA square, and magnitude of JdB, this JdA is equal to root over REB square plus XEB square. So, if these magnitudes are inversely proportional to the kVA, that is fine. But then another condition may be put, that about the quality of the impedances, quality of the impedances of the leakage impedance. If XCA by REA, this angle of these impedances are also suppose same, got this ratio. So, leakage impedance angles, they are same, and magnitudes I will put them in the inverse ratio, that is JD, I have seen that this is JDA is 1 by, that is JDA is equal to some K times 1 by SA KVA rating, so JDB magnitude, same K type 1 by SB, that we have seen. Then I am saying that okay, if you just meet these conditions, then you may think yourself, Achha, what happens this square root of this square plus this square and square root of this square plus this square can be chosen in such a way that these ratios are the ratios of the currents, the way I told. But what about the quality? Is it going to make any difference? The answer is yes. About the quality also you have to think a bit. Now, what it is? Look back. I will draw it here. So, here the thing is very simple idea. This is EA and this is your REA, XEA, and this is your EB, equivalent circuit referred to secondary side of both the transformer, and this is your I 2 and here is your secondary load, this is Z 2. Okay. And this is, these are all phasors, I am not putting bar, magnitudes I will put that modulus sign IB. And let us assume that EA is equal to EB, that is the case we are studying. These two phasors are same. Now, voltage across each of the impedances I will calculate. This voltage is suppose V2. Then what is the voltage across JDA? It is equal to EA minus V2, which is same as voltage across JDB. Because same V2 and EA is equal to EB. So, same voltage has come here. So, suppose the voltage across JDA and JDB are same, let that voltage be denoted by some voltage VAB. Suppose I say. So, I draw that first. Here I will just give you the idea. Suppose this is the voltage across this and across this, that I have drawn. If the qualities of the impedances are same, then IA will be lagging by some angle theta, not power factor angle. Okay? What is theta? In this case I am telling, this case. If this is the case, then I am defining tan inverse XCA, that is the power factor angle of the leakage impedances, XCA by REA, which will be same as tan inverse XCB by REB, and that let it be theta. or say theta E, some equivalent impedance, its power factor angle, it will be IA. And similarly, where will be your IB? IB will be also lagging VAB by the same angle theta E under this condition. Therefore, your IB will be which transformer I took more? This is 2 kVA IB. So, its current will be less. So, this is your suppose IB, I will clean it. This I will write it as IB and this one will be your IA. It will be like this. What is the current supplied to the load? IA plus IB, phasor sum of these two, but they are co-phasal, IA and IB. So, current supplied to the load will be this one, this plus this, I2, is not? This will be the thing. What is the kVA supplied by this transformer? It is V into IA, where V2 into IA. Achha, here I write kVA to load is equal to V into I2. kVA supplied by transformer A will be how much? This voltage is V2 means this voltage is V2. This transformer is delivering what is this voltage? V2, V2 into IA. So, this is V2, this is V2 into IA and kVA supplied by transformer B is equal to V2 into IB. And if the quality of the leakage impedances are same, it will be the algebraic sum of these two is this one, that is then V2 IA plus V2 IB will be equal to V2 I, algebraic sum. That will be the case. Clear. Therefore, you see, I will not only demand that that the leakage impedances should be inversely proportional to their kVA ratings, but also I will say it will be very nice if the qualities of the leakage impedances are also same. Then tan inverse XC by REB is equal to tan inverse XCA by REA, and you will get the most desirable thing. For the example we have taken 6 kVA, 4 kVA and 2 kVA transformer, we have paralleled them. If the leakage impedances of these two are in the ratio 1:2 or 2:1 that we have seen, and also the angles of each of these leakage impedances are same, qualities are same, then your output kVA will be also 6 kVA, and that is the best thing. Apart from, of course, this polarity should be same, voltage ratios should be same, that is the first thing. Second, if we go much deep into it, then we have come to this conclusion. We will carry on with this in the next class. Thank you.